Record to the cloud. Excellent. Welcome back, everyone. Um, Hope everybody had a great weekend, that you have great fun doing your assignments and quizzes. I'm sure you had a blast. Thank you very much for everybody who has already submitted. I do want to remind everyone the deadlines for every quiz and assignment is the Sunday of the week that it was delivered. We are flexible. We can give you extra time, and we will do a tally of all the assignments that have not yet been completed and send you privately via email your instructions on how to proceed. For the quizzes, if you didn't submit one or more of them, you may have already received an email saying, "Hey, you have an additional chance." The final submission deadline is indicated in that email. It's not Sunday, so it's before the end of the week. We're giving you a second chance. We would prefer to keep everybody more or less in track during the course, but life happens, and sometimes some of you may get delayed. So we're happy to provide this additional days to complete the quizzes and the assignment. Some of you may receive notifications that the assignments have not been submitted and so on and so forth. Sometimes what happens is the collection of emails that will go out is constructed as you are completing your assignment. So probably, you completed the assignment after the list was constructed, and then it was sent out, and that's the reason why you got an email. If you got an email and you believe that it was an error, feel free to send me a message through Slack. I can verify and confirm with you that I see the actual submitted quiz. Sometimes I think it has happened only once out of 250 or so students that we've had. You may complete all of the answers but not click the final submit button, and that is a reason why you get the notification email. So you just need to go back in and click and submit. It's as simple as that. Okay, so today we will discuss feature engineering, and we will do our usual dynamics, in which we will discuss feature engineering in the first part of the class. I will take a little shorter amount of time this time so I can complete all of the notebooks for session 03. So there are two notebooks there, very short ones, and there's one larger one for session 4, which I would like, if not complete, get a good head start on that. I will allow questions as we did before. Every 20 or so slides, I will make a pause and open the floor for questions. So if possible, please, I will ask you to write down your questions, and then we can discuss them during the specific periods. And last but not least, if you are able and willing, please turn on your camera. It's just easier for me to talk to people as opposed to talk to my computer screen. Okay. So let's talk about feature engineering. Okay, so feature engineering, we're on chapter 5 of Design Machine Learning Systems, is it is over here and over here. So what we're going to discuss today are techniques by which we can extract the information content of our data and make it available in a shape and form that will help our learning algorithms. Not every algorithm will be able to directly utilize all of the data that you throw at it. Okay, so some algorithms will be able to do so. There are certain algorithms that are very, very flexible, and you need to do very little to your data, and they will take it in. Some other algorithms will need certain transformations. So for example, some algorithms will not understand categorical variables, and we will need to transform them into numerical variables. Some algorithms will benefit from having certain distributional assumptions met by the data, and that will help you achieve better performance. We'll see how to do that. And some algorithms will be affected by size, right? So in certain cases, certain algorithms will ascribe more importance to variables whose values have a larger magnitude than other variables. So the typical example is if you have a data set that has amounts, money amounts in the millions, and you have interest rates that are in the percentage point, so you can express these things as something dot something else, or 0.01 equals 1%, these tend to be very small numbers. So this discrepancy between millions and percentage points or decimals will induce certain variability in your modeling results. So scaling is always a good option. Having said all of this, we need to be careful because when we started, we said our algorithms need to learn from certain data. And when we evaluate our algorithms, we cannot have an algorithm that was trained on the data that will be used to evaluate it. Okay, if we end up in a situation which we're using data, evaluation data, validation data, or testing data, and we use it to train, we will be kidding ourselves. We will not get appropriate or correct or reasonable estimates for error in the testing set because we would have already seen what we were meant to learn, right? So that doesn't make sense. It's just an illusion. That performance will not be a real performance estimate. Okay, so let's talk about featureization. Um, I started the conversation by saying, look, feature engineering is a process by which we extract information such that it becomes useful for our learning process. But back in the day, and now this is starting to become a bit of old history. A few years ago, let's say about 10 years ago, there was this big revolution of deep learning. Okay, so deep learning were a collection of algorithms that were based on the notion that a neural net will be able to learn fundamentally anything that has value. There's a very fundamental theorem called the universal approximation theorem, and it is a very powerful result. It says that a neural net is able to fit or to approximate to an arbitrary extent. So we can approximate something to, whatever, as close as possible or as close as we want using a neural net of arbitrary, with a single fully connected hidden layer of arbitrary length. We don't have an assurance of how long that hidden layer would be. And the consequence of this result, of the universal approximation theorem, it means that if we're able to approximate any Borel measurable function, we can fundamentally approximate anything that has value to us. Okay, so these Borel measurable functions have very nice characteristics. They are, among other things, they can include functions that are continuous and differentiable, and nice behaved functions. But in the world that we live in, most of the functions that we will be working with are Borel measurable, which means that with a neural net, we can potentially learn anything. That's a very powerful result, right? If we can just take this artifact and push our data into this artifact, and we can learn any pattern from our data, that seems like a very tall order. So the first complication is I said, well, this universal approximation theorem works for a neural net of arbitrary width. We don't have an assurance if there's going to be a few hidden nodes or if we have a million hidden nodes. And this has a lot of implications because if we have a million hidden units, that means that we have a fair amount of weights to learn, and therefore we will need a very large amount of data to learn these weights. Okay. So then somebody else came along, and these people are now very famous, and they said, look, instead of having an arbitrarily wide neural net, let's stack neural nets together, right? So we stack a neural net, and then we stack another one on top of it, and then another one on top of it, and so on and so forth. And and let's use certain optimization criteria. And what we learned out of these exercises is that neural nets will turn out to learn using the first few hidden layers, a representation of our data. And then the last few layers will be used to learn the actual task, classification in this very specific case. Okay, so If that is the case, then, back in the day, we were saying this is the end of feature engineering, right? Because if our models can just learn and we throw a lot of data to our models, they will just learn the right representation that fits the problem they're trying to solve. And then the last few layers will just learn the classification task. And that seems like a utopia, right? It is magic, right? What I'm just described is magic. You take a box, you pour data, and on the other side, you get the results that you want. Okay. So unfortunately, this doesn't work like this, and there are many reasons for us to avoid this magical approach. The first reason is data can be expensive to get, right? We may not have enough observations. We may be working in a domain in which it's difficult to actually get a million observations. Maybe we are in the healthcare field and we only have a few observations, 1,000 cases. Okay. So that is one holdback. If we don't have enough data, we cannot train one of these very complex models. Second of all, is we may be asking from our models things that neural nets cannot provide. Explainability is one of these things, right? So we may want a model that is explainable because within the environment that we are operating, we need to provide explanations. Okay, so maybe we want to shy away from neural nets and use another modeling approach. Third reason might be, well, okay, we have the data, we can use whatever model we want, but then you will need a computation to produce one of these models. And once you produce them, these models may become brittle. Right. So one thing that we know is that certain deep learners, if you change the input data, then the entire configuration of the network will change and our results may also change. So maybe we want additional robustness, that's one, or we want to save in cost. And now, this deep into the course, we know that saving in utilizing a certain model may not necessarily be the amount of money that we're paying for the model. It might be time, right? So we may be using a model that takes a very long time to produce inferences, and that model doesn't fit our purpose. Okay, so there are many reasons why we want to step away from this paradigm in which we have a deep learner and it will help us just do magic, right? And do without feature engineering. Feature engineering is something that you will do, at least for the foreseeable future, anytime that you're trying to model a certain phenomenon. Now, um, what is feature engineering? Feature engineering is the process of choosing what information to use and how to extract this information to a format that is usable by machine learning models. Okay. The purpose of it is to transform and represent features so that their information content is best exposed to the learning algorithm. And I really like this second definition in the sense that what we're doing is we're not making up data, we're transforming it in such a way that it becomes usable by our learning algorithm. And I'll give you very specific examples in a few minutes. Okay. So feature engineering can include many transformations. And I'm just going to walk through a few of them. Okay. The transformation of a feature. The first thing is we take every single feature, and I'm going like this because we are thinking that in our data set, a feature is going to be a column in a table of our data set. Okay, so from now on, whenever I speak about a feature, it is going to be a variable or in the values that it has that we are going to send in to our learning algorithm. Okay, so we can transform one feature at a time. How? We can standardize it, so we can uh, subtract the mean and divide by the standard deviation. If we perform this operation, the resulting feature will have a mean approximately equal to 0 and a standard deviation approximately equals to 1. So if we have, let's assume, a bell-shaped distribution of values, that bell shape can be centered around any value. It doesn't need to be 0. With standardization, we will bring it back to 0. And in terms of the dispersion, it can be as wide or as narrow as we want. We will make it a standard dispersion. Standard deviation equals to 1. Okay. We can scale in other forms. We can circumscribe the range, right? So we can make our values all between the numbers 0 and 1 or -1 and 1, some suitable range. We can center. We don't need to divide by the standard deviation. We can just simply move everything into the 0 mark. We can use robust statistics. So if we have many outliers, our mean will be distorted by the outliers, right? So if we have 100 numbers that are around the value of 1, and we have one number that is 200 million, and we calculate the average of them all, the average will not be around the value of 1. It will be shifted to the right because of this outlying factor. We can reduce this effect by using robust statistics, such as the median or the interquartile range, right? So that way, we reduce the effect of outliers when we center and scale. We can take the log. The log transformation, you will come across it 400 million times. So it's super common. The log transformation, what it does is it makes small values very large or much larger, and it makes large values much more muted. So if you have a lot of observations in a range between, let's say, 0 and 1, and you want to increase their visibility, right, that you can apply a log transformation. And if you have a few values that are very large in size and you want to reduce their scale, then you can apply a log transformation. Okay. Now, another transformation that you can do is an equivalent re-representation of a feature. Okay, so some algorithms will not take categorical features, right? We will need to convert them to numbers. And the easiest way of converting them to numbers is to create additional variables that take binary values, 1 or 0. So the way we do this, it's relatively simple. So let's say that we have a feature that is color, and then there are three colors: red, green, and blue. Full stop. Okay. So we have our feature set. We have one column that has the values red, green, and blue, and we're trying to apply a logistic regression model. Logistic regressions will not work with red, green, and blue. They need numbers. Okay. So we apply something called the dummy variable transformation, or depending on the model, we could also apply the one hot transformation. And the way that this looks like, I'm going to start with one hot, is we create a new variable called blue, and it will take the value 1 whenever the color variable was blue, and it will take the value 0 otherwise. Okay. We repeat the procedure and we create a variable called red, and the same thing, right? It becomes 1 whenever the value of color is red, and it becomes 0 in any other case. And lastly, we will take the value blue. Okay, what I have just described is the one hot encoder transformation. Okay, every single value is represented by a column, and every column will have 1 whenever the value of the original variable was, whatever the column header was, and 0 in any other case. Okay, this works very well, except for linear models. Linear models, coming from statistics and doing a fair bit of linear algebra manipulation, requires that not every single value is encoded as in the one hot encoding mechanism. So what we do is we just exclude one. This means that instead of having red, green, and blue as the columns, we will only have red and green. Just to be perfectly clear, this is necessary in linear models, in linear regression, logistic regression, because these models require linear independence in their features. It's a statistical procedure, and this is one of the requirements. Okay. Binning. We discussed binning last week, and that is if we have a set of values that are numbers, we can create bins of numbers. Okay, so we can take all of the numbers between 0 and 10, 10 and 20, 20 and 30, just of equal length bins. So that is one option. We can create our bins such that we have more or less the same amount of observations in each one of the bins. So that will give me bins of different sizes, of different widths. But when I measure their frequency, they will tend to have more or less the same numbers. Okay. So binning or discretization is one way in which we are creating an equivalent representation or an equivalent encoding of the original values. Okay. We may be interested in observing the interaction of two or more features, right? So, such as a product or ratio. And this is very common in interaction studies and statistics. We may want to create additional features by multiplying one feature times the other. And this is very convenient, for example, if we want to see the effect of red, having the color equal to red whenever we're using, for example, a logistic regression model. So we take red times height, and that will capture the effect of having the color red on something that is a feature for our model, right? On the height in this case. Now, usually we don't do the cross product indiscriminately. These things can, if you multiply all of the features times each other, this product grows exponentially, right? So you end up with a lot of features at the same time. And usually the cross effects are not that strong. If you believe and you test that there's a cross effect that is very strong and you want to highlight it, that is where you apply this interaction mode, right? In any other cases, you may want to step away from it. So you want to be judicious as to when you create these features by multiplying two features together. And most of the time, what you will be doing is you will take a categorical, perhaps one encoded feature, times another feature. It could be categorical or non-categorical, right? But one of them will generally be categorical. Okay. Then you can do something a little more complicated, like a functional relationship. There are a couple of them. One that I think it's important for you to be very aware of is called principal components analysis. So, principal components analysis is a very fundamental and it's a very powerful technique by which we take a data set, we calculate its correlation structure, and we perform a transformation of the data set such that we create variables that are uncorrelated among each other, right? So the first variable is not correlated with the second one, and the second one is not correlated with the third one, and they are not correlated among themselves. And the first variable will capture the most variability in the data set under linear transformations. Okay. So basically, what we're doing is we are extracting and summarizing the correlation structure of our data. And then, as analysts, we may decide to keep a subset, a subspace of the principal components, right? And we do so because we want a better representation, a more succinct representation. Parsimonious is the word that I should be using. A more parsimonious representation of our data. Okay, so parsimony, if you're not familiar with the concept, is a concept that comes from statistics, and that is we should aim to use the least amount of information to provide the explanation that we're looking for and nothing more, right? So we want to be as simple as possible, but not simpler than that, right? So we're trying to reduce the number of features that we use to produce a prediction. Okay. So principal components analysis is one option. The other option is it's not latent dirichlet analysis. Linear discriminant analysis. Sorry, linear discriminant analysis is an old technique. It also comes from statistics, and it performs a partition of the space, but in the direction of maximum separability. So we have a few classes, we can re-express our data in such a way that the data points of one class get as much distance as possible from the data points of the other class. Okay, so we'll walk through some of these techniques in a few. Okay. Now, common features in feature common operations in feature engineering. Okay, the first and most important operation probably is handling missing values. Missing values are super common. You will find them wherever you go. Even values that you thought would not be missing, you will find them missing. Okay, all missing values are of different nature. The first thing to remember is missing values may be there, may be missing because someone doesn't want you to know that value. Okay. So if I'm making a survey and I'm using this survey as a feature set for a given predictor, and part of my survey includes what is your income, maybe people don't want to disclose their income. Okay. And they will leave it blank. There's no question about it. It's not that they don't have income, it is that they don't want to disclose their income. So in this case, the value is not missing at random. Okay. It is missing not at random. Sorry. And the case is there is information in that missing value, right? Somebody decided not to disclose income, and that may be because they don't want to. Full stop. Another possibility is that the value is missing not due to the value itself, but to another observed variable. Okay, so maybe people don't want to disclose their employment situation, right? So they don't want to disclose that they are looking for a job, maybe they're in between jobs, and so on and so forth. And because of that, they don't disclose their income. Okay, so the fact is not that they're concerned about their disclosing their income; they are concerned about not disclosing that they are not currently employed. Okay, so there is a knock-on effect, and when this happens, we call those type of missing values missing at random. Okay, and then there's a third variety. Something happened. There was a failure in the communication between the observing instrument and the database that is recording the observation. So in that case, it was an actual error. It was an operational matter that didn't allow the recording of a certain reading, and it was not meant to happen. It happened completely at random, right? So these are the actual factual missing values that we didn't expect, and but they are there, right? Connection issues, file quality issues, you name it. Any type of operational issues may appear as missing completely at random. Now, what do we do? Okay, so the simplest thing to do is just to remove the missing values. But then we need to decide either we remove the column or we remove the row, right? We cannot just simply remove the missing value. We need to decide if we remove the column or the row. If we remove the column, it means that we're going to remove the entire feature. And this could be appropriate if we have a very large amount of missing values. And that would say you're aiming for 95% of missing values or like a really dramatic percentage of missing values. Okay. In that case, it may be appropriate to remove the column. In other cases, we may want to indicate, hey, most of the values are missing, maybe 70% of them, but then we have a bit of information and we'll discuss how to tackle those cases in a second. But removing a column, do remember that you are removing the entire information content of that feature from your feature set. So that is that can be a costly procedure, costly from the informational sense. Okay. You could also think of removing the row. Okay. Um, if the row contains a lot of missing values, right? So let's say that you have 10 variables and there are 9 of them missing, then it might be appropriate to remove the entire row, right? If you have 10 variables and only one of the values is missing, then you probably want to keep that row because you still have a fair bit of information about that observation in your assay of data, right? So in that profile that you have created for that observation, there's still 9 very valuable data points. So we need to think about something else. Okay. That something else is generally called imputation. So when somebody tells you, hey, please impute your missing values, it means plug something wherever you see a missing value. Okay. So there are many different ways of approaching this. The simplest way is just to use a default value. Okay. So if you have a missing string, instead of displaying NA or null as in SQL or pandas, you can fill them with quote unquote, right? So there's nothing in the middle. There's a value called nothing, right? And that is how I represent a missing value. So in some cases, that may be a reasonable approach. That is just a change in representation of how we talk about or think about missing values. We can use a statistic like the mean, the median, the mode to fill in the missing values, right? So that may be appropriate if you believe that the value that you're plugging in is makes sense to be substituted by an appropriate mean. So if you're measuring temperature and suddenly you're missing an observation at 3 p.m., you could take, the previous 5 days temperature measured at 3 p.m. and use that as a missing value imputation. Okay, that may make sense because I know that going from the past five measurements at 3 p.m. till today, it kind of jive. So I'm not reading from December. I'm not reading over the past 5 centuries. It's just the past few days. Okay. Now there are things that don't make sense. If you're missing a price, right, and you take the 5 days, the previous day's closing price, you average them and you plug that in, that may not be appropriate, right? Because prices don't have any stability that kind of indicates that the mean is the best predictor of the missing price. So for those cases, you can use domain specific knowledge. So in finance, it's very common to say, hey, if you have a daily observation of prices and you're missing one, use the previous day's observations, last available price to plug in the missing value. So you don't take the mean, you take the most recent one. Okay. And there's a theory behind that, the efficient market hypotheses and information theory and so on and so forth. So there are good reasons to use this. Okay. Another way that you can do is you can fit a model, right? So you can take your other features. You know that there's a certain relationship between your features. You can fit a model. Let's assume you fit a linear regression model or a logistic regression model, and from that model, you use it to impute your missing values, right? So you fit the model and you use the results of that model to impute your missing values. So that's a better way of approaching it because you're trying to maintain the relationships, the structure of the relationships in your data set. Okay. Depending on the complexity of your model, you will be able to capture more. But generally, when you're using a model to impute missing values, you want to use something that works fast and that is simple to understand, right? So it doesn't require a lot of explainability. Linear models are a good choice. You can use something like KNN, like K nearest neighbors. That is also perhaps a more time-consuming choice, but it is also easy to understand. And then it depends. It depends on the context of your problem. If you know a priori that there are certain relationships that need to be maintained, apply the appropriate model to impute those missing values. Okay. Another choice that you will need to make is let's flag imputed values or not. Okay. So you have a variable. That variable may have holes, right? There are missing values in there. But once you impute them, maybe you also want to keep track of which values were actually observed and which ones are synthetic values that you're using for imputation. Okay. Um, how do you decide any of these things? You will create a pipeline. In that pipeline, there will be an imputation step. That imputation step will have all of the different choices that we have just discussed. Are you using a mean? Are you using a median? Are you using the mode? Are you using a model? Once you impute your missing values, will you add an indicator, yes or not? Okay, so you have that construct as a part of your pipeline. You take your entire pipeline, including the classifier, and you test it, right? And you observe the performance of this entire pipeline, which is, as we know now, our model. And the choice that maximizes your performance metric is the choice that you should take. Okay. So we don't determine these things a priori. We determine these things experimentally by observing the effect that it has on model performance. Now, one general recommendation is avoid filling missing values with possible fixed values. So, for example, the missing number of children should not be filled with zero or which is a possible value, right? So there's a very strong distinction between null, I do not know how many children Jesus has, right? Versus zero. This is a statement in which I'm saying Jesus has zero children. We're saying two different things. Okay, so whenever you're imputing missing value, be mindful that whatever you plug in there will or could have meaning. And if so, maybe we want to continue consider flagging imputed missing values. Okay, so that is where it becomes very relevant. Okay, another observation, scaling. Okay, the objective is to obtain values of similar magnitude. So I talked about standardization and I also talked about scaling. Um, the nomenclature here can be a little confusing. Generally, scaling refers to the scale, the size of the values for any given feature. And but most of the time, you will apply scaling after applying centering in an operation called standardization. So standardization is equal to centering plus scaling. Okay. Now, scaling the same as standardization, most likely. I haven't taken that course, but most likely it's the same thing. Okay. So I have a few formulas to describe this thing. Now, scaling is super common. And most of the time, if you don't know if you need to apply it, apply it. It doesn't hurt. It is a very common transformation. I don't know of any cases in which applying scaling to your variables will actually hurt your performance unless you know that it is a very expensive operation. If you have a very large amount of data, then perhaps scaling all of your data can be costly. Um, the most important thing to remember about scaling is that it is sample based. Okay, so the denominator of the scaling operation, it's a standard deviation, and when you subtract the mean is something that is based on a sample. Okay, but the name of the game is we don't combine training and validation and testing sets. Therefore, when we compute the standard deviation, when we compute the mean, that mean and standard deviation should be computed on the training set and the training set only, not on the entire set. You cannot pre-compute scaled features and then send them into a pipeline, because what you would be doing is taking distributional information about your entire universe of data and then putting it into your training sample. Okay, so the most important thing to remember about scaling is that you need to be careful not to combine data sets. Okay, now there are many flavors of scaling. Min-max scaling will keep your data between the range 0 and 1 because it will basically take all of your values, subtract the minimum value, right? So that will kind of like bound all of your data at 0, and then divide by the range, right? The range is the maximum minus the minimum, and that will basically make your range that was 0 to infinity all the way to 0 to 1. Okay, that doesn't fix the fact that if you have a high concentration of data and you have a couple of outliers, you will end up with the same distribution in the 0 to 1 range, right? It doesn't fix that issue. You can scale to an arbitrary range. Sometimes it makes sense to scale to the range -1 to 1, -10 to 10, -5 to 5. It depends on your context, right? So there are certain conventions that may be useful to maintain. So you can use something like this to scale to an arbitrary range. Okay, so the range can be whatever it is you decide it to be. -1 to 1 is a very common choice. You do that if you want to retain the negative sign, if it makes sense. So in certain contexts, temperature, for example, temperature can be positive and negative. So you may want to retain that fact that whenever in the normal scale something is positive, in the scaled values, you retain that variability. Okay, and then the standardization or normalization, sometimes called, and it is this operation over here, right? X minus the mean divided by the standard deviation. If you have outliers, you can always change the mean for the median, right? So this can become the median. The median is the observation from which 50% of the observations are above that number and 50% of the observations are below that number. And instead of using the standard deviation, you can use the interquartile range. Okay, so this is the difference between the 75th percentile and the 25th percentile. So 50% of the observations are in that middle section, and that is the thing that we use to as an estimate of variability, right? Of variation. Okay, so I'm going to clear all my drawings and move on. Okay. We may also want to re-encode or recode our variables. Okay, so we discussed now the dummy variables, and we discussed as well the one-hot encoders. And I don't think that there's anything that I want to add on those, other than dummy variables you will generally use in linear models, or anything that sounds like a linear regression or a logistic regression model. They will use dummy variables always. And this is because of a requirement, a mathematical requirement in which you're start by solving an optimization problem. That optimization problem has a matrix involved in it. That matrix needs to be invertible. Okay, so therefore you need to use linearly independent features, and one-hot encoded features are not linearly independent. In English, this means that one-hot encoded variables, if I know n minus 1 variables, I will be able to determine the nth variables. So in my original example, I had red, green, and blue. If I observe a certain observation and it's not red, it's not green, it needs to be blue. Okay, and that is where the independence is broken, right? If I remove the blue, then we have a set of linearly independent variables. Okay, for other models, specifically neural nets, I'm sure you're going to play around with those quite a bit. You can use one-hot encoded variables, right? And other models, booster models, bagging models, and so on and so forth, can also take in one-hot encoded variables. Okay. Discretization is this concept of binning. Okay, so this there are many names for it. Discretization, quantization, or binning is the process of converting continuous features into a discrete feature, right? So continuous means that we take all of the real number range, so it doesn't stop. I can add a number like square root of 2, which has an infinite decimal expansion. I can add a number like 3 or pi or whatever number I want. And in the discretized sense, I have a discrete, a countable set of values. Okay, so we can discretize by equal lengths, equal weights, or any other arbitrary buckets, right? Sometimes, for example, in the cases of years of birth, we may want to use marketing type of criteria, right? So I label, I don't know, people born between 1950 to 1969 as baby boomers, and then from 1970 to 1980 Gen Xers, and then from 1980s to the 90s millennials, and so on and so forth. Right? There are many definitions of these things. So that is a discretization that has semantic value. We can attach meaning to it, or there's a cultural significance to it, but it doesn't follow a mathematical distribution or a statistical distribution or anything along those lines. Okay, so that is also another way of discretizing your data. A disadvantage of discretization is that it introduces discontinuities at the category boundaries, right? So we don't have a nice flow of numbers. We are artificially cutting this very nice and smooth flow into discretized bins. Some authors, one of them, Max Kuhn, Khun, and please do remember that name. Max Kuhn advises against discretization. You lose information, you lose the granular information of having a continuous variable when you are binning, when you are discretizing. Okay, so he says, in the measure possible, avoid it. There may be many better ways of doing it. Okay. So the reason why I say Max Kuhn, remember that name? He's a brilliant author. He publishes quite a lot. He speaks very frequently. He's an R person. He has written very influential libraries in R. And whatever he writes, it's worthwhile reading. He's a very clear writer and very well organized type of material. Okay. I think we have discussed all of this. We discussed collinearity. So I'm going to skip through that. Okay. If the original value is missing, then all dummy variables are missing. Okay. If we have a certain setup, red, green, and blue, and then one of those variables are missing, the one hot encoded version of color would have all of the values equal to zero, right? So in that case, we are representing something that we don't know, or rather, it is not red, it is not blue, and it is not green, right? So we want to be careful with these cases. We need to tell the algorithm, and we will need to do so, what to do in cases in which the value is missing or if it encounters a value that it has not yet seen before. Okay. And this will happen to us. And our algorithm will determine the categories based on the training data. But there is no assurance that all of the categories will be represented in the training data because when we perform the split, we generally split based on the targets, not based on the features, right? And if we do something a little more complex, like cross validation, then we will get a fair bit of mixture. And in some of those random samples, we may end up in a situation in which the training set contains red and green, but it has never contained blue, right? And therefore, we will need to tell the algorithm if you encounter something that you have not seen, treat it this way. And we'll see it in the practicum how we do these things. Okay. Um, it is generally a good idea to consider a category called unknown, and that is what I mean, right? So if we find something that we have not seen before, we need to label it. Now, in some cases, unknown labels may refer to samples that do not belong together, right? So sometimes, in the context of our problems, unknown samples will have different categories. So in the case, for example, of e-commerce, right? We may be classifying new products. They come in a batch. We get an Excel sheet with a whole bunch of different product names, and we need to classify them. This is a cell phone. This is a pen, and then suddenly you end up with a shoe, and you end up with a necklace. Okay. So I haven't seen them before. I can label them unknown, but then the consequence of that is that shoes and necklaces will end up in the same bucket. And that may not be appropriate for my context because in my context, I am running an online shop and my shoppers want to see shoes on one side and necklaces on a different side. Okay. So one function is that we can use a hashed value of the descriptor, for example, right? And use that hash value to create new categories, and off we go, right? So we just use the hash value and send to different places and separate these unknowns into a more granular categories. Okay. Feature crossing. We discuss interaction terms. Those are the cross products. I don't think that there's anything special about this slide other than um, this note here. This type of transformation is primarily intended for numerical data. Still, it may be applied with categorical data after being transformed into dummy variables. Okay. So what I mean by this is we cannot multiply categories, right? So we need to have the categories transformed into numbers. Once you have everything converted into numbers, then you can multiply to your heart's content. So these interaction terms, this cross products, if you will allow us to detect the cross influence of two variables in our model. And because we're generating them as a product of two variables, we need to first do a conversion from categorical to numerical if that is the case. Okay. I'm going to pause here to see if there are any questions. We covered a fair bit of terrain. We're on slide number 23. I saw a hand. think, Tala, you had a question. Yes, please.
Uh, so my question is that in case that we have null values, for example, we have a network and the network has a couple of nodes, and some of the nodes they just don't have that specific feature. It's null. How you're going to handle it?
Okay. So we said you can either plug a standard value, you can just quote unquote. That's one option. You can use a convention, right? So you can use, in the case of prices, I said, well, I use my expert knowledge to plug it in. So maybe in your context, you can look around. So you have a node in a network, and that node may be connected to other nodes. One option is look around, take the average value of the surrounding nodes to 1 degree and plug that value in, right? So that's
No,
one option.
sorry for interruption. Imagine that that specific node just doesn't have that specific
Value.
feature.
Mhm,
Yeah, and it's normal.
mhm.
Uh, I mean, we don't need to replace it with anything because the nature of it is no. Is it okay
Oh,
to
yeah.
fit it into the model
Yeah,
like
yeah.
this?
It
Oh,
is. It is okay. It is okay. If something is expected to be null, there's no reason to dispute it, right? To impute it.
uh-huh. Uh-huh.
You need to encode it. You need to represent that nullability somehow. And if your model allows null values, there's nothing else to do. If your model does not allow null values, then you will need to impute it and then flag it with a flag that indicates this was missing or not, right? And then the imputation procedure will be context dependent on the model that you're creating, right? It is depending on the context and the model that you're using, the classification model, if you will.
Okay, thank you. Thank you so
My
much.
pleasure. My pleasure. Any other questions? Sneha, please. I think, yeah, we cannot hear you. No, no, sorry. I'm gonna address a question in the chat as you're trying to figure out your mic, or if not, feel free to type it in the chat. It might be easier. Still confused on the difference between dummy variables and one-hot encoding. It is the only difference. So Anoop, I read somewhere the one difference is that for a feature with n categories, one hot will have n variables, while numbers will have n minus one, and that is the difference. They are not the same. The main difference is one hot encoding does not produce a linearly independent data set, and the dummy encoding does produce a linearly independent data set. You need to use dummy for linear models. You cannot use one hot encoders because it will give you an error. Okay. Anoop, please.
Uh, uh, Thanks, Jesus. I just, yeah, so I kind of understood what you said, but I'm still like, so how do you practically do it? Like, is it the same process as you described for one hot encoding? Then,
Yeah.
like, the process is the same, but then
And
there
just
is
remove
one.
one.
Okay. Oh, okay. So, I
Yeah,
mean,
just remove one. You can choose if it's the first, the last. I don't think that any algorithm allows you to be very specific as to which one you remove, but
okay.
it really doesn't matter. We'll see how to do it with code.
Okay.
Very
Perfect. Thank
simple.
you.
Yep. Any other questions? Nika, maybe you want to type it.
Yeah. So
Oh,
can you hear me now? Yes.
yes, yes, brilliant.
So I still don't understand the use of discretization.
Okay. So, uh, sometimes we don't care about the actual value of a variable. Okay. I don't care if a person, I may not care if a person is 40, 41, 42, 43, or 44 years old. I just bucket them all in middle age, right? And we call that discretized version of age middle age, right? So I may care about, what stage in life they're in. Are they teenagers, early adults, middle-aged people, older adults, and so on and so forth? And for those purposes, I don't really care if the age is, 38 or 16 or whatever. I am ascribing values to these kind of generational buckets, if you will. Okay, so that's one option. The other option is does it matter if tomorrow it will rain, or I'm predicting that it will rain 1 centimeter or 1.025 centimeters? Most probably not, right? I don't care about that accuracy of the prediction. I just care if it's going to rain, 0 to 1 centimeter, 1 to 2, 2 to 3, and so on and so forth. So that is another example in which I can apply discretization. Okay,
Thank you.
my pleasure. Okay, so feature crossing. Any other questions? I didn't see any other hands. Just going to continue. Okay. Multivariate transformations. So we discussed two transformations, principal components analysis and linear discriminant analysis. Let me see. No. Okay. So principal component analysis, I'm going to use this slide because it has a lot of space. It's something like this. Imagine that you have a cloud of data. Okay. So these are my data points, and they are measured in two variables, x1 and x2. It doesn't really matter for the sake of example what x1 and x2 are, but they can be, I don't know, income and age or something like that, right? So one thing to notice is generally there is a correlation structure in this chart, right? So we know that there's a line around here that kind of like mimics the behavior of this cloud of data, right? So one thing that I can do is I can take this line, this direction, and I can use it as an axis, right? So when we think about an axis, basically what we're doing is we're projecting our data into the axes, right? So let me just change back to red. So when I say this specific observation, I'm just going to make it very large, has certain coordinates. What I mean is if I project this line to the x1 axis and this other line to the x2 axis, these are my coordinates, right? So this is the specific version of x2, and this is the specific value of x1 that gives me this point. That is the notion of coordinates, right? So there's nothing weird about it. Now, I will take this space and I will rotate it, okay? And I will rotate it, I will take the picture and I will rotate it like this, okay? And my new data set will become something like this, right? So I have taken the entire data set. This picture and that picture, the red picture and the blue picture, represent exactly the same data. But this transformed data set, the first direction follows the direction of the largest variability. And the second direction is statistically independent under the normality assumption, and also follows the second direction of most variability. And this is a very powerful result because if I have a 20 dimensional space and I perform principal component analysis, I get a very nice set of re-expressed data, and I can choose how many dimensions I want to keep if I want to retain a certain amount of variability. This is a consequence of the model. Okay, so once I perform the rotation, I may decide in this very simple example to ignore this direction and only keep a single dimension because it will retain a fair bit of my variability. Okay, so what I have done in this example is I studied the correlation structure of my data, I rotated my axis, and then I, Jesus, the analyst, have removed one of the directions because I want a more parsimonious representation of my data. And it turns out that this data, this reduced form of data, will retain a certain amount of the variability that I am observing on the original data set. Okay, this procedure is called principal component analysis. You will see it in many different applications. I think it's one of the most commonly used transformations. It's a linear transformation. It has very desirable features, and there's something that I would encourage you to read a little more on. It requires a little linear algebra and spectral transformations. Don't get scared about the words. It's really a very intuitive way of understanding your data, and you can extract a fair bit of value out of it. Now, Another form of transformation has to do with linear discriminant analysis. I'm going to use another color. And basically, in linear discriminant analysis, you have certain observations. I'm going to draw them in a dark color. And then I have another set of observations over here, right, that are of a different class. That's the reason why I'm using a different color. Okay, so using linear discriminant analysis, what I can do is I can find a certain direction of maximum separability. So under this direction over here, if I rotate my axis, I end up with all of the orange dots on one side and all of the black dots on the other side. And this is a consequence of a classification algorithm called linear discriminant analysis. And it is like a byproduct. This separability observation is what you get. Okay. So let's look at something else that is also a byproduct. Okay. So the next one, and this you will encounter many times in your professional life, is called an encoding mechanism. Okay. The problem setting is as follows. I have a certain amount of textual data, okay? And I'm going to use this text over here as my training sample, as my training corpus. The problem that I will originally want to solve is the following. I take a certain window. Let me say I'm going to take a window of 4 words. Okay, so I'm going to take 1, 2, 3, 4. I'm going to remove the last word, and I'm going to say, with these 3 words, training neural nets is, I want to predict what the plausible next word is, right? Now, once I'm done with that problem, I'm going to take another sample. I'm going to take the next window of 4 words, right? So the 4 words are going to be neural net is computationally intensive, okay? So I'm going to take the first 3 words, this thing, and I'm going to try to predict the 4th word. And I repeat, I always move my window by 1 word, and I'm always trying to predict the next word. This type of problem is a supervised problem. I have labels. I always have the words that I want to predict. And but I don't need to do a lot of work to produce these labels, right? So it's called sometimes semi-supervised learning because of this characteristic, right? That labels come automatic out of my sample. Okay. Now, how do I craft this problem? Okay. The way to craft these type of problems is I take a dictionary. This dictionary can be based on your sample, or it can be based on something else, on the English language, Wikipedia or something like that, right? And you take a certain amount of the most common words. Let's assume that there are 10,000 words in your dictionary, okay? So I'm going to take 10,000 words. Every word is represented by a place in this vector. So training might be the first word, neural nets might be the second word, is the third word, and then computationally the 4th word. Okay, so every phrase I can represent it as a vector of 0 and 1s. Okay, so that is going to be my input vector. Okay, so you take your entire corpus, you decide the 4th window, the 4-word window. You say, hey, the inputs are going to be, let me just clear my drawings. The inputs are going to be, first word, second word, and third word, maybe. I don't know. And these numbers become 1, 1, 1. And on the other side, I have another 10,000 long vector, and it will have one position, which is the predicted value, right? So this is the position that I want to predict. Yep, so that is the framing of the problem, okay? And I will repeat this many times. How many times? As many times as you can, right? You take the entirety of Wikipedia and the New York Times and the LA Times and the Washington Post and the blogs and the yada, 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 and you perform this prediction problem, okay? What you will get, oh, sorry, I didn't talk about the model, okay? The model is a neural network model, okay? So we have a neural net. There is a hidden layer and there's an output layer. This is the simplest architecture that you can do these things with. You can actually complicate it a little more, but let's assume that we're going to use this thing. Now, notice that I have 10,000 inputs and I have 10,000 outputs. Okay, so I'm going from the same space as an input to the same space as an output. But what changes is this thing in the middle. We only have 300 positions in the middle. Okay, so what I'm doing is I'm taking a language that has 10,000 words in it, I'm squishing it into a 300 word language and then decompressing it on the other side. And what I'm interested in is in this compressed representation. I actually don't care about the prediction problem, right? I care about the compressed representation. These things, oh, I have the word here, are called embeddings. So whenever somebody comes to you and says, hey, I want the embedding representation of this corpus of text, what they're thinking is there was at some point a model that was trained like this. I would like you to take the corpus of text, plug it into that model, and obtain for every word the representation in this 300 dimensional space. Okay? Why do we do that? Because this representation of language is very efficient. First and foremost, we are reducing the dimensionality of the problem. We're reducing the complexity of the problem, right? So we have 10,000 variables at the beginning, and we reduce it to 300 variables as a consequence of this procedure. And the second thing is once we have a reduced representation of these words, that representation may have characteristics that are useful for us. So it turns out that in the embedding space, words that have, I wouldn't say similar meanings, but adjacent meanings tend to be kind of geometrically in the same regions. So the words football, soccer, cricket, baseball, basketball, and so on and so forth, they will all appear in a similar region. The words pizza, spaghetti, tacos, memelas, whatever else, will appear on the same on a region in which all of these words are very near together. Okay, and the same goes for any subject area. So there's a fair bit of information that comes out of embeddings, and most of the language models that you will use will require some form of transformation into embeddings. This is only one out of many ways of embedding, creating embeddings for your text, but this is probably the most common one, or the one that is used most commonly. Okay, let's move on. So this is another feature transformation procedure. It is not simple. It is something that you will encounter though several many times. Okay, I'm going to pause here. I know we're not in slide number 40, but this is a complex matter. Any questions on this? No? Okay, excellent. So let's move on. Data leakage. Oh, Sui, please.
Sorry, I just found the button. So in terms of this, I had kind of heard of like the concept of, like, for example, say you have an AI that's meant to assist you in your work or whatever it is. And like Snowflake, for example, has this where they basically have a large language model that is specifically trained on your usage of language, and you have like a semantic model. Is this kind of what they mean by it essentially? Like if you only have 300 bins, you would want to have the network that's trained on your data so that it actually, like, if we say, for example, in my work, there's an entity called opportunity that is related to an entity called contact and an entity called transaction, but they might use it differently. Is this kind of how you would create a large language model that is responsive to your specific like software applications?
Yes and no. This is the first step. So for the
Mhm.
application that you're describing, generally what happens is once you have the representation of your words in the embeddings, it is sent to another model that has a transformer architecture and perhaps a final set of layers that perform a certain task. When you say, well, I want to contextualize it to the language that I'm using, there is probably an exercise in which you were requested a few samples of the language that you are using, right? That is used to train the last portion of that fairly complex network, right? It's a transformer model. It's not necessarily a network, but it is trained, it's fine-tuned using those examples that you have. So this is the first step. This is just to transform language into an appropriate form. Then there is a larger model that has been trained using a transformer architecture. And then there's your sample that is plugged in to that transformer architecture. And that is how you get the service that you are describing. It is beyond the context of this course, but it's a fascinating subject. It's not necessarily complex. Hopefully you will get a chance to work deeper with it.
Awesome. Thank you.
My pleasure. Anup.
Yeah, thank you. So I really like this slide because I kind of now feel that I understood a little bit of the LLMs and how do they do it. But I just want to make sure that I understood right. So when you said about the input vector, 10,000 like long input vector and corresponding. So it's like a, so in this case, you also mentioned that, okay, let's say you have 3 words and you predict the 4th word. In this case, I just want to make sure that in that case, the input vector will have 3 ones, right, in the positions of the 3 words. Is that correct? Or
Correct.
okay, that's
So
just I want to
one
confirm that.
and one,
Okay,
right? And then the output will only have one in a certain position.
because you're only predicting 1 word.
I'm
So
only predicting one word. Yeah.
okay, thank
And
you.
the context that I gave at the beginning is just one out of different things. I mean, you can predict the last word, but you can also choose to predict any word within the phrase.
So do they
So
also typically change the in the real context when they're doing this learning? Do they also change instead of 3 words, 3 words, and then 4th word, let's say like 5 words to
yeah.
6 words, and so on and so forth?
Yeah.
Okay.
And the size of the input vectors, the size of the output vectors, and the corpus that you use to train this thing. So if you are in the medical field, it is more convenient for you to use a corpus that comes from medicine than general language corpuses. Or if you're in the legal field, it's much better to use legal cases, legal documents, than to use general language cases, that sort of stuff. Okay.
Okay. Thank you.
Sucharita, please.
Yeah, so how does this compression or decompression of this 10,000 to 300 happen?
How does it happen? Yeah, it's a brilliant question. So these arrows are actually one arrow that points to each one of the 300 units. Okay. Each arrow represents a certain weight. And when this number is equal to 1, it is multiplied by the weight and then pushed as an input to a nonlinear function. Okay. Then the output of that nonlinear function is then sent to the output of this classification layer. And this classification layer also has a nonlinear function. Okay. How does it happen? You optimize the network, right? You solve this problem for all of the words in your corpus, and the resulting weights are the things that will drive precisely the formation of these embeddings. Okay, so you solve the optimization problem. You use backpropagation, just like any other neural net, and then you determine the weights, and these weights are the ones that you need to determine the embedding for each one of the words.
Oh, okay.
Okay,
Thank you.
it's as simple as that. Okay, any other questions? No, let's continue. Data leakage. Okay, so I've been going on and on and on data leakage. Data leakage refers to the situation in which we have contaminated our training data with data that we should have not yet seen. The easiest example is what I said earlier today. We are combining data sets by performing this mean and standard deviation computations, and we want to avoid all of that, right? As well, when we have time correlated data, we may want to be very careful of how we split our data, right? So we don't want to do a random split, because by shuffling our data, we may end up in a situation in which we know things about the future when we are in the past. We can fix this by doing a time-based cross-validation procedure. We take older data first and then predict the next temporally consistent data set. So we take a month's worth of data and we predict the next week. Then we take 2 months worth of data and we predict the following week, and so on and so forth. Okay. You can complicate matters a little more. You can be very careful in your selection and your sampling criteria and keep certain buffers around your samples, right? So you shave off 2 weeks before and after, and you take the month in the middle, and that becomes kind of like a unit for computation. Then you can mix and match all of these little units, but you need to be careful that you leave these buffers before and after so that you ensure that nothing from the future is brought back into the past. Okay. Other cases are scaling before splitting. So you want to split always your data before scaling, applying a transformation. So most machine learning libraries will help you fix that issue. Some machine learning libraries will allow you to fix that issue, and if not, by now you will be able to write the code to actually do that. Now, filling missing value, missing data with statistics from the test split is also a source of data leakage. So maybe we're not scaling, but we're imputing missing values. If you perform the imputation procedure at the very beginning and you say, oh, I'm going to use a model, okay, fine, you are contaminating by the use of that model your testing data set into your training data set. Okay, so we may want to avoid those conditions. Poor handling of data duplication. If you have duplicate instances, data leakage can also happen, right? So if you have the same instance twice in your data set, you perform a random split, and one of the instances ends up in the testing set, the other instance ends up in the training set. That is another case. So deduplicate your data if you have suspicion that there are duplicate entries in there. Group leakage. So it may be similar to duplicate leakage. So you have groups of data that repeats themselves, right? So remove those duplicates. It's the same idea. And then leakage from the data generation process, right? So the sampling mechanism may induce some duplication. So patient data in critical condition is duplicated because more tests are run. So if you have a patient, you have two patients, for example, and one of them is not in critical condition, the other one is. The patient that is in more critical condition many times is tested several times precisely because of the condition in which they are in. So therefore, you may end up with duplicate or near duplicate samples within your data set. Okay. How do you detect data leakage? So measure the predictive power of each feature. So you can do this by mechanisms such as feature importance. We're going to see this in a couple of days, how to measure features. We can investigate the data generation, and if we can derive a valid explanation. So if we see that we have a highly predictive feature, we want to make sure that it makes sense that this feature is highly predictive. If we have a theory, if we have additional knowledge about the relationship between the feature and the target, we may be able to justify that relationship. If we don't have a priori knowledge about these relationship, then we may be seeing a fluke, an error, right? Perform ablation studies, so remove one feature at a time. So we have our entire data set, we remove one feature, and we observe if the model continues performing well. This is very similar to performing a feature importance analysis. If removing a feature causes that the model's performance to deteriorate significantly, investigate why that feature is so important. So once again, can we come up with a good reason to understand the relationship between the feature and the predicted value? And pay attention to new features added to the model, right? Generally, you want to be suspicious about very good results. So if you get an extremely good result, it is very likely that something went wrong, and that something going wrong may indicate that you have contaminated your training set with testing data, or that you are not accounting for a relationship that you probably should have accounted for. Okay, how do you engineer two features? First, avoid many features. Before I go on, Omar, please.
Yeah, so just a quick question regarding the data leak. So when I do transformation and fitting, I just want to clarify one point. When I do those scaling, standardizing, everything all on the training set, right?
Correct.
The test, I shouldn't be touching it. Now, when it comes to the imputation and adding maybe one hotspot and all of these stuff, so or one hot encoding, do I do them for both or just the training?
You do it for both, but you do it at different times, right? So you do it based on what you know. And here's the thing. When you train your model, there will be values for imputing missing values. There will be means and standard deviations for scaling. And then you take the test set and you use the values that you learned on training and apply them on the test set, right? You don't train on test, right? But you already know, the model has already learned. So you always apply the procedures on both sides, but you only learn from the training set. Does
Okay.
that make sense? So you only calculate mean, standard deviations, imputation values on the training set, and you apply those values on both sides, on the training and on the testing set, because you will need to apply them on the testing set as well.
Okay, when it comes to application, it's not going to be done. I mean, I'm assuming when I do the amputation, whatever kind of maybe functions or something that I
Mhm.
created on the side, they
Mhm.
should be also applied to the testing. That's
The
basically what you're
testing
saying.
set, exactly so.
Okay, because Dimitri, I guess you've mentioned that you're going to end up having different features, or there's like a feature difference between the training set and the test set. If I
There-
do implementation on one and not the other one, is that correct?
Yes,
Yes,
exactly
so
so.
since it's Dimitri, yes, it's supposed to be on both sides, but you have a transformation mechanism that you will apply on testing set. But you train this transformation mechanism on your training set, okay?
I got it. Okay, okay. I appreciate that. Yeah, I just wanted to clarify that point.
That's
Okay,
fine.
cool. Thank you so much. Yeah.
My pleasure. Excellent. So how do we engineer good features? We want parsimonious models. Don't models, machine learning models are not like blenders. You don't throw everything at it and then just turn it on and it will crush them, right? You could do that. Sure, you will not get good quality models. So in the measure that you can help your models with a selection of good quality features, your models will generally perform better. Too many features cause overfitting, so you may inadvertently be producing overfitted models, right? They have learned the noise in the data, not the actual signal. More features require more memory to serve a model, which can increase hardware requirements and costs. It can increase latency. So you want to remove features, and useless features become technical debt, right? So if you have useless features, uninformative features, you will need to remove them at some point, or they may be inducing noise and they degrade your model performance. So if a feature is not useful for prediction, regularization should get rid of it. In practice, it might be just simpler to plug the feature away. Okay. And to do that, we can use mechanisms such as feature importance. The first mechanism, I'm going to take 10 more minutes of your time, then we'll go on a break. The first mechanism is called permutation feature importance. Okay, so permutation feature importance is very simple. We have a model, we have trained it, and we take one feature, shuffle all of its values, and then observe the effect on prediction quality, on prediction performance. Okay, if the effect is very large, it means, or it can indicate that that feature is very important. If the impact is not very large, it means that that feature is not very important. Okay, given that we are shuffling our values, we induce randomness, we want to repeat this procedure many times. You can run this 20, 30 times per feature.
Fix this.
I'm sorry? There is sorry, I got distracted. So you need to run this procedure several times so you can calculate an average effect on performance, and of course you can also calculate the deviation, right? In this case, these bars indicate the standard deviation of performance. This results, by the way, are based on the Give Me Some Credit dataset that you will use tomorrow, and these are transformed features. Notice that I took the log of certain features, some other features are not transformed, and so on and so forth. So I'm trying to determine which features are the better features of this model. Okay. Another option is to use partial dependence plots. Partial dependence plots are basically a relation between a certain feature and the predicted probability of the event that is of interest to us happening. Okay, so how does the predicted probability or score, I should use the word score, change as I move one of the values of the features? And that kind of gives you an intuition about how these features and the probability score, the scoring mechanism are related. Okay, you can do this with one or two variables, features at a time. You cannot do more than two at a time. It doesn't make sense. Three-dimensional pictures don't really show you that much information. So these two procedures are more or less heuristic procedures. They're kind of rule of thumb, things that people have been using for a long time. But they're not necessarily based on mathematical results, like purely mathematical results. Both of these models and methods, and the two more that I'm going to discuss in a few minutes, are called post hoc explainability methods. And they're called like this because post hoc implies the fact that we have already trained the model and we don't know what that model was. It could have been a neural net. It could also have been a support vector machine. It could have been a logistic regression. We don't know. We want methods that apply to any model that we have as an underlying model, right? And we will apply them after the fact that we have trained the model in a post hoc manner. Okay. Now, some limitations of the permutation importance mechanism is that it's not clear if we should be using training or testing, right? And it depends on what is it that we want to examine. If we use training set and we shuffle and we repeat and so on and so forth, basically we would determine which feature is more important during the learning process. If we use the validation or testing side, then we would be examining which feature is more important at the time of inference. Okay, it can be biased by unrealistic values, right? So I'm shuffling. There's no assurance that the resulting combination of values per observations are realistic. We may end up in a situation in which we have a high net worth individual with a very low monthly income, something like that, right? So it may be unrealistic from that sense. And if we have correlated, highly correlated features and we shuffle one of them, the information is still contained on the other, right? So highly correlation features, highly correlated features will tend to have the same information content if we shuffle one of them. The other one still retains that information content. So we may not be able to completely address if that feature was important because the other feature was still present. The limitations of partial dependence plots, it's a graphical device. We can only do this for a couple of features at any one time. It assumes independence between explanatory features. So when the features are correlated, then the distribution is weird. It doesn't give you good information. Okay. And there may be heterogeneous effects that could be hidden by the partial dependence plots, right? So things that don't flow smoothly are shown as a smooth change in the PDP. So these are very simple artifacts that we probably want to use with care. They're nice diagnostic tools, but they are not the end story. More powerful tools include local surrogate models. So one question that may arise is, okay, so we have a certain set of results. Okay, the gray results are the negative instances. The light blue regions are the positive instances. We have come to this decision boundary, this region, through a random forest algorithm. We cannot necessarily explain very well what is going on, but I just chose random forest. It could be boosting algorithm. I don't know, some algorithm. Now, one idea that occurs is we could potentially select a dot, this yellow dot that we have over here, and we say, hey, for that specific observation, I want to understand where this or why this prediction of it being a negative result was given to that specific observation. Okay, so what I do is I select this specific observation. I overweight the observations out of my universe of observations, the ones that are in the vicinity of that original dot that I'm interested in, right? So I give them more weight and I underweight everybody else. And then I fit a naturally explainable model. In this case, a logistic regression model, right? So you see the line here, or maybe you look very closely, you will see a line over here, and that is the result, the decision boundary of the logistic regression model. And through this model, I can locally explain why this observation was given the prediction that it was given. Okay, so that is the procedure called LIME. So it's called local interpretable model agnostic explanation, and it is one out of potentially many methods under the local surrogate models, right? So we use a surrogate, right, a substitute model to perform the explainability component. And then finally, we have a more advanced method called SHAP. And SHAP is based on results from economics, from game theory. And a few years ago, about 10 years ago, Lloyd Shapley actually won the Nobel Prize in economics, and because of his contributions to game theory, in which he was saying, hey, if we have a cooperative game, we have a bunch of people playing a game with a given objective, I want to determine what is the contribution of each individual player to the overall objective of the game, to get the highest score. And to do that, he came up with a computationally intensive algorithm, and there's a lot of math in it. In our context, our players are features, right? So we have a team of features, and they're trying to play a game. The game is to predict a certain class, right? So we're in the classification setting. And every player will have a certain contribution, and we want to determine the contribution of each player. We perform the SHAP values analysis, and we can come up with this result. The SHAP value analysis, I won't go into the details. There's a very nice book by Chris Molnar called Interpretable Machine Learning. It's in the resources, in the references. So this book over here, and it's free, so you can just Google it. These things usually have a URL. They got lost in the translation somehow. But this book is really worthwhile reading. And he explains the entire procedure. It's a combinatorial, computationally intensive procedure, but the result of it is that we can get for individual observations, the contributions of each one of these features to that specific prediction. And if we take all of these results across all of the predictions that I did, I can add them up and I can come up with a global explanation of how this algorithm works in terms of feature importance. Okay. This is probably the most advanced method in terms of feature importance. It's not a silver bullet. It will not solve all of your problems, but it will help you solve the question, which features are more important for this specific prediction and which features are more important in general across all of the predictions that I have made. Okay, so it's a very nice algorithm. Highly recommend that you read into it. Okay, there are limitations. Both of these procedures, right? For Lime, there's a number of difficulties. How large is the neighborhood that I should be looking at, right? How should I choose my surrogate model, right? Can I bias my results? The answer is yes, I can bias my results. I can lie with Lime, right? And come up with the feature importance that I think should be coming out. And SHAP values are difficult to interpret. The natural inclination is to interpret them as if they were the beta coefficients in a linear regression. That is not the case. The SHAP the interpretation of SHAP values is given here. So given the current set of feature values, the contribution of a feature value to the difference between the actual prediction and the mean prediction is estimated by the Shapley value, right? So by it is the difference to the mean as opposed to the importance or the coefficient in a regression of that feature. And it is computationally intensive. Unless you're using tree-based method or linear methods, this procedure will take time. it requires a fair bit of computation. And if you are using complex models, it will require a fair bit of time and computing power. Okay. I'm going to pause here before we go on a break. Any questions? Banks, yes. Banks use SHAP values and LIME as explainability. Banks have, I don't know about healthcare, but banks have a very strong regulatory environment on their models. So regulators will ask a fair bit of their models if you're going to use them for calculating the amount of capital that a bank needs to hold. And typically, banks will shy away from using machine learning methods directly to compute those capital values. They will use statistical models that are very robust and easy to defend, but they will also use machine learning methods to challenge those initial models. So when we started the class 3 or 4 sessions ago, I was discussing many model thinking. This is what I mean, right? You may have a non-machine learning method to determine a certain result. That doesn't stop you from using machine learning to produce alternative models that can challenge this original model that you have over here. Okay, Maria, please.
Yeah, so thank you. When encoding data, like categorical data, so we split the data set into training, testing. And what if we don't find the same like categories in testing than in training? Like, what's the best approach for that? You said that you were gonna discuss it, but I think maybe I missed it.
We will discuss it in the implementation. So you need to
okay.
add a flag and say, hey, if I encounter a new value, first option is break. Show an error, throw an error. I don't know what this is. And this can be an actual thing. So for example, if you're doing gene expressions, you may encounter a new combination of RNA encodings and so on and so forth. But if you encounter a new letter, that is something that you shouldn't have, right? That there's only a limited number of letters that you can do. But there are cases in which you can encounter new things, right? So I'm selling shoes and suddenly I encounter socks. Okay, fine. So that's valid. Maybe I want to issue a warning and put it in the unknown category or do something else. And I'll show you where to put these things in the functions.
Okay, thank you.
Okay. Any other questions? Comments? Going once? Twice? Okay. Let's take a 10-minute break and I'll see you in 10 minutes and we'll continue with Python. Okay. Thank you so much. Okay, so before we jump into Python, I just sent via Slack a couple of recommendations from this individual, Max Kuhn, brilliant author. Whatever you find from Dr. Kuhn is worthwhile reading. The first one is this book called Feature Engineering and Selection, and it is an entire book on feature engineering. Everything that I have discussed is contained here. It's a very, very insightful discussion on how to select the features for your models, how to go about the problem of saying, hey, I have 15 a data set of 50 different features. I want to predict this variable. I don't want to use 50 features, right? I don't think it's necessary. How do I come up with the 5 or 10 that I need to use to get a parsimonious model? It discusses different types of features, different types of examination procedures, and it also, if you go all the way to the bottom, and many of these things are what we discussed here in class. Interaction effects, those typically are a little bit tricky, so you may want to look into that. The other ones that I found very interesting is, imputation of missing value and then working with profile data. What happens when your features are actually a profile of individuals, right? So these features may have a correlation structure within them. And then how do you go about the actual process of selecting features? This is beyond the scope of this course, but if and when you do this professionally, you will need to come up with an approach, a strategy by which you will select the features, right? Do you add one feature at a time? Do you start with all of your features and start removing each one of them? Saad, the link is via Slack. You can find it there. And And then global search methods. This is something fairly advanced in which now you use genetic algorithms to optimize the feature selection procedure. So it's a very, very, very good text to look into feature engineering. And the other one, I'm sure that some of you are come from the world of R, and R is a beautiful language. If you're data scientists and you're working in the healthcare field, for example, it's going to be your your bread and butter. It's a very powerful language, perhaps not as common as Python, but nevertheless, it has a very long tradition of data analysis circles. And there's this brilliant book called Tidy Modeling with R. The book is worthwhile reading, even if you don't work in R. Just following through the discussion of how to build a model, how to test your data, how to understand the decisions that you need to make. It is a single model explained throughout the book. So the Kuhn and Silji, Julia Silji, also brilliant data scientist, worthwhile following her. They go through the beginning all the way to the end, and at the very end, they give you a gift, and this is the gift that I was referring to. It is this table in which you have different pre-processing methods: dummy variables, serial variance, imputation, decorrelation, normalization, transformation, nonlinear transformation, so the Box-Cox type of transformation, and then the different types of models that you can apply it to. This is our naming convention. So this is a decision tree, bagging model, bagging tree based, BART, boosting tree, and so on and so forth, decision tree, linear regression, logistic regression, multi-layer perceptron, so neural nets, and so on and so forth. So, support vector machine. All of the models that you will see during the courses, if you don't know where to start, this is a very good table to say, hey, I may want to apply these pre-processing methods before jumping into my classification problem. Okay, so these are the two references that I want to share with you. Now let's do a bit of Python. Okay. I'm going to work with 3 notebooks today. Hopefully I will have time to actually walk you through all of them. The first notebook that I'm going to start with, it's 03 sampling. Let me just make my font a little bit larger. 03 sampling is something that we discussed last week. And it has to do with sampling. I'm not going to walk you through what this thing does because we have done it many times. We load our usual libraries: Dask, NumPy, Pandas, Glob, OS, and so on and so forth. And I load my data. The data, there's nothing magical about the data. I look into my features data. This is the features data that we created last time. So if you run 02 data engineering entirely, you will end up with this data. Now, the main aspect here is I want to create a sample, and I want to use stratified sampling. So the first thing that I'm going to do is I'm going to show you what DF does. DF is a data frame. It's now a Pandas data frame. It contains ticker information with the prices that we have seen. Nothing special about this data frame. Okay, contains the dates and so on and so forth. If I simply run df.sample with n equals 5, I will get a equally weighted random sample of rows. This is a standard behavior in Pandas. If I do dataframe.sample with a number, I will get that number of rows. If I make this 25, I will get 25 randomly selected rows of my data frame. And if I run this 5 different times, every single time I will get a different set of results. Okay, so no surprises there. There's nothing stratified about this sample. I'm just random sampling rows of the data frame. And I want to be clear on this. The philosophy here is every row is an observation, every column is a variable. So therefore, the standard behavior in Pandas is to randomly sample n observations out of my data frame. Okay, so that's the reason. Now, the second thing I want to do is I want to use this construction that I had done before, and I just select a few tickers. The ticker count. So by doing this, I have selected a few tickers. Notice what I'm doing over here. I take a simple sample. So the sample, okay, I'm gonna take it by steps. This part over here will select my unique tickers, right? So there's the ticker variable, and I just basically take the unique values and convert it to a list. From that list, I want to select a sample, a random sample of 30. So this variable will contain 30 randomly sampled tickers. Now, given that I have fixed my random seed, we know that it's really not that random, right? So it is something that looks random, but it's not really random. Okay, so I have selected 30 tickers. Now, this part over here will subset my data set. Okay, so what this part means is when ticker is in the list of sample tickers, then it becomes true and keep that observation within my data frame, right? So I enclose it in square brackets, and that is how I subset by contention. Okay, so if something contains something else, that is, if the tickers is in sample tickers, then that condition will be true. And for those rows that the condition is true, I will keep it in my sample. So now DF will contain a random sample of 30 tickers, right, across the board. Okay. Now, if I were to do something like this, so now I have my 30 tickers and I sample a fraction, 10% of my observations, and I will call that the simple sample. Well, the first thing that I should notice is that out of 120,700 and something observation, I will get 12,000, right? So I have sampled 10%. There's no magic there. I got the right number, right? The way I got to this output is very simple. I take simple sample dt dot shape, so that gives me the first tuple, this thing here, comma df dot shape, and that gives me the second tuple, and that is how I get this result. Okay, so there's no magic, but what is important to remember? If I count my tickers, okay, so I'm going to take from my 30 randomly sampled tickers, I take the value count of each ticker. So I'm going to count the number of times that each ticker appears on the original data. And I plot a bar plot, right? I will get this shape. Notice I have TNC, AIM, WST. They're in decreasing order. Then I have a plateau or something that resembles a plateau over here, CRMT, TEF, and then continues going down. Okay, so that is the general distribution of my tickers in my overall universe in DF. When I look at the same thing, but now for my simple sample, I get somewhat similar, somewhat distinct distribution. So notice, for example, CRMT and TEF, they increase. So CRMT and TEF, CRMT is lesser, and then the other one is larger. And that doesn't necessarily hold as clearly in here. CRMT is higher than the count of TEF. And if you start looking into the general distribution of the sample, it will not follow the same shape. I can force it to follow the same shape, right? And I do that by stratified sampling. I will use the group by operator that we have used now many times. Instead of having an apply or a sign or anything else over here, I will take a sample, right? And I will assign it to stratified sampling, and then I will create another chart that is similar to the one below before. And this one will guarantee that you have exactly the same distribution of ticker count. Okay, so the main thing to remember here is to perform a stratified sample over whatever variable you choose. You can use the group by operation and then sample. So basically what we're doing is we're creating groups. The groups are created by tickers. Within each ticker, I take 10% of the observation, and that is how I perform a sample that has been stratified by ticker. You can substitute ticker to whatever variable is important for you, and you get the same results. Okay. So that is the first thing. If you want to do it in Dask, you can do it as well in Dask. I just basically lump everything into a single operation. I read my Dask data frame, that's this line over here, and then I group by and I apply my sampling procedure, right? There's nothing other than group by, apply, and then my anonymous function calls the sample procedure. I compute because I need to compute. This is a lazy execution library, and then I just remove the index, right? I bring in the index back into the data frame, and I get very similar results to what I was looking for below. So hopefully there's no questions in here, but I'm more than happy to take a question. Sneha, please.
Can you hear me?
Yeah.
Yeah. So I have one question in this notebook. So when you were reading the files, you were using Dask, right? But then you converted the data frame into the Dask data frame into the Pandas data frame using compute, right? And
Using compute, yes, at the very top.
so why did that? Why not then read the files using Pandas at the first place itself?
Oh yeah. No, I did it both ways. So the first discussion is in Pandas, and then the second discussion is in Dask. The reason why you want to do it in Dask, and it's not specifically for this data frame, this data set, but if you have 200 million observations, if you want to try to do this in Pandas, it will take you a very long time. So you might as well do it in Dask because you can parallelize the computation. So I just wanted to demonstrate how to do it in Dask. The decision is mostly efficiency, right? So if you have a very large data frame, use Dask. If you have a regular to small size data frame, use Pandas. That is my recommendation.
So what is the definition of small size?
Of what? I'm sorry?
Large. What is the definition of small size or large size?
I'm sorry, I cannot get the. What is the definition of what?
Small size or large size data.
Oh, what is the how much how small is small or how large is large?
Yeah.
It depends on your computer. When you see your computer is slowing down, that is too large. Because obviously, if you have, I don't know, sometimes I rent 64 gig in memory with 16 cores, just because I don't want to use Dask and so on and so forth. Just pay for the additional processor. If you're working your laptop and you don't have 64 gigs of memory, you probably only have 16 or 32, then it's contingent on the system that you're working with. I don't think that there's a clear-cut definition.
Thank you.
My pleasure. Okay. If there are no other questions, I'm going to move at light speed to 03B. Okay. Pipeline, this notebook, what I'm going to do is I'm going to demonstrate how to use pipelines in scikit-learn. This is very important. Pipelines will help you keep your training and testing set more or less clean, and they will be your friends. This is the typical way in which you will be building models. So by now, you probably have already trained a few models, and you will continue training models over and over and over again. Okay, so I'm going to load my, oh, by the way, I updated this notebook. It is not the same one that we had last week. I just updated it today. If you haven't done so, please download a new version from the production repo. The main branch is now updated. Okay, now the first chunk does nothing weird, right? So we read the Parquet data frame, we make it a Pandas data frame because of the compute, we set the index, and we remove any missing information. Now I will need, notice, okay, I got this pesky notice over here, okay? And so it's an interesting observation. I had not run this notebook before, but Jupyter is telling me you are not loading the .env extension for the first time. So what is happening is the kernel was not shut down, right? The kernel continues to exist. It has things in memory. My Jupyter notebook right now is contaminated with the things that I did before. Okay, so you want to avoid that contamination, and you see something like this. The easiest way to do it is just restart the kernel, right? So it restarted the kernel. You may get confirmation. Do you really want to restart the kernel? And now that I run this, this legend will actually disappear, right? And it will disappear because now my kernel is fresh. There's no .env loaded, and so be it. Okay. So so we have df, our pandas data frame. I will load another file. This is also contained in the same Kaggle file, the zip file. It is just the additional CSV that comes at the base directory, some symbols symbols valid meta .csv, but in reality, I only need a few categories to work with. What I will do to that file is I will read it. This line over here just basically creates the file name with the entire path, right? And then in this line, I'm going to read the file, and then I'm going to rename some of the columns, okay? So the columns that the only column that I'm going to rename is symbol, and I'm going to rename it as ticker. Okay. Why? Because I want to perform a join. And I understand that you've already taken a SQL course. Show of hands, you've taken SQL? Yeah? Okay, brilliant. Okay, so then I'm going to do my square parentheses over here. So this guy here will return a data frame. This guy here will return a renamed data frame. A data frame, right? So on any data frame, I can open square parentheses, give it a list of variables, and it will return only those variables. So I'm only taking ticker, listing exchange, and market category. And I'm going to just silence that for a second. And I'm going to show you what this looks like, okay? And this is what my data looks like, and my category data looks like this. I only have ticker, listing exchange, and market category, right? The things that I said over here. Okay. Then I'm going to take my data frame, which was this guy over here, and I'm going to join it with category data frame in the very similar fashion to what you did with a left join in the SQL course. Okay, so if you remember, this left join will contain all of the observations on the data set on the table on the left-hand side, and only the observations on the right-hand side that are matched to the observations on the left-hand side. Okay, so this is one of the fundamental joins in SQL. And in Pandas, the way you do it is with this command. Okay, so I do df.merge. So this is my left-hand side, df. My right-hand side is category df, so cat df. I'm going to use ticker as my joining variable. So in the left join command in SQL, when you say this table left join this other table on, this is the on, right? And then how do I want to perform this merge, right? What is the type of join that I want to use? And I can use a left join, a right join, an inner join, or an outer join. And hopefully I'm not confusing anyone with these words. If not, these are very simple words in SQL literature. You can Wikipedia the reference for them. So I'm going to perform a left join, and basically what this will do is it will keep all of my data in df and only the observations on cat df. And what does this look like? Like an extended data frame. So I just joined and expanded my data frame. I'm sure some of you are realizing that what I'm doing is I'm denormalizing my data. So when we looked at data engineering, we said, hey, you will get data in two tables, and for machine learning purposes, I need a long table with all my observations in a single place. That process, we called it denormalization, and it is exactly what I have just done, okay? And I did it through a join. Now, I have my denormalized data. I will need to start doing some pre-processing steps, and then finally I'm gonna create a model, okay? So the first thing that I want to do is I want to see, what columns I have. These are the columns that I showed above. And I'm going to create a few features that I require. Okay. The features are going to be very simple, right? The first thing I'm going to create is the returns. Obviously, this is something that you should have done in your homework, and if not, well, here is the answer. The second thing is I'm going to identify positive returns. Why? Because I'm interested in positive returns, right? The way I do it is I create a lambda function that multiplies the number 1 times a comparison. Is my returns column greater than 0 or not? This thing will return a true or false, but I know that my algorithm will require numbers, right? Because scikit-learn is pesky in that sense. It doesn't take true or false. It requires numbers. So what I do is I multiply 1 times true or false. 1 in Python, 1 times true is equal to 1. 1 times false is equal to 0. Okay, so that is basically what I'm doing. All right, I'm setting a flag 1 if the return was positive on that day, 0 if it was not positive. I calculate a couple more features, just the difference between the high and low price. For those of you in finance, this is sometimes called realized volatility. It is the amount of variability that there was in a trading day, right? The highest price and the lowest price. And then I take the open and close price, which is another measure of realized volatility. How much was the price at closing versus how much it was the price at open. Okay. Then notice how I am concatenating my operations, right? So up until here, I have an expanded data frame, right? I have expanded it with returns, positive, high, low, and open, close. Okay. Then I'm going to group by ticker, right? And I will assign a certain target variable, okay? I will use this shift function. We have used it in the past, right? So instead of looking into the past to create a lag, I want to create a few forward-looking variable, right? I want to get in this target an indicator if tomorrow my return was positive. Obviously, I want to make money. I want to observe the value of my stock today, and I want to be able to predict if the value of the stock will increase or not tomorrow. Okay, that is the target that I am creating. Okay, and then I do some modifications, meaning I reset my index. I drop any indices that were put in, and I drop any missing values from my target dataset. This is a requirement from scikit-learn. It doesn't make sense to send in a missing value in your target variable. It will throw an error. Okay, so I'm just going to run this so you can see what we get. And we get this very long data frame. It's our original data frame extended with our categorical variables. Calculated returns, positive return, high, low, open, close, and then the target value. Notice that it's 1 when my return is positive on the next day, and it is 0 in other cases, right? So to have a negative result, negative result, negative result. So these guys are 0. Okay. Okay. So this is just my data set. Then we're here for a few things. So the first thing that I want to create is, let's create a standard scalar object from scikit-learn dot preprocessing. So we take the entire library, and there's a module within that library called preprocessing. Inside there is a standard scalar class. That is the one that I'm going to import. And then this class, I will instantiate it. Okay, and I do this in this line. Okay, on that class, I'm going to perform this operation. Now, what is returns? I am asking myself. And I would like to know what that is, because I think that this is going to break. Yes, I have nothing in returns. Okay, so I probably deleted these by mistake. But returns is my returns vector. Let me show it to you. Okay, so returns is this thing over here. If I do returns.describe, okay, I will see the exploratory data analysis of my variable called returns. I have 353,400 something observations with a mean that is not necessarily 0, it's about 4%, and the standard deviation that is 21.47. Okay, so very large standard deviation. We have a lot of variability in this data set, and we have a center component, like the central measure. It's about 4%. Okay, now we said that we wanted to standardize this thing. Okay, so I'm going to create a variable called returns, and I extract it this way. I'm actually going to print it at the end, okay, so you can see what it looks like. These are my values. We know that underlying pandas, there's a NumPy implementation. And when I do df data frame, select a certain subset of variables dot values, I will get access to the underlying NumPy array. So this is a NumPy array, right? So I can check the type, for example, like this, and it will tell me it's a NumPy ND array. Okay, so returns now contains that. So I reperformed this thing that I wanted to perform at the beginning, and I get an error. Notice the error that I'm getting. I am expecting a 2D array, but got a 1D array instead. And you will get this error many times. Okay, so you can reshape your data using this command if your data has a single feature, or this thing if it contains a single sample. Okay, so in our case, it contains a single feature, so we can use this thing over here. So I'm just going to take it, copy it, and paste it here. Okay, and that is my standard scalar. Okay, now in Jupyter, we will always get these representations of the standard of any scikit-learn object. In this case, we are using a standard scalar which has been fit on the returns distribution. Okay, so let me show you how I notice. If I hover my mouse over this information icon, it tells me that it has been fitted, and actually, if I click here, it will show the standard scalar documentation from scikit-learn. So it's a very convenient interface. Okay, so this is the standard scalar. Now, I want to see the effect on my descriptive statistics. So what I'm going to do is I'm going to take this standard scalar, which has already been fit on my returns data. Just to be perfectly clear, that means that the standard scalar already contains a metric or a number for the mean. So I can display it like this, and the mean is the 0.04, so the 4% that we looked at before, and it was calculated on the returns distribution. Okay, so it is already contained in the standard scalar object. So I'm going to use the standard scalar object to transform the returns itself, right? So I have fit using returns. I'm going to transform now using returns. I'm going to put the results in another NumPy array called scaled returns NP. NP stands for NumPy. And then I'm going to convert that into a data frame, okay? And I'm going to describe it, okay? There's an error here because the reshape thing. Yeah, so I'm going to copy this reshape.
I think Jesus just use double brackets instead. I've tried it and it worked. I should advise that too. Instead of changing it every time at the very
I
top,
can yeah I can yeah absolutely, you can do it at the very top, and you can do it double brackets or reshape it. Either way works. Okay, I'm going to remove the columns because there are no columns there. Made a mistake, but I want you to see this. Okay, this is the the scaled version of the returns array. It now has a mean that is a number to a power of, multiplied by 10 to the power of minus 19. So there are 18 zeros and then this number 5. For all practical purposes, this number is 0. Okay? And then the standard deviation is very close to 1. So it's 1.12345 zeros and then a 1. This number is 1 for all practical purposes. So what we have achieved is a procedure that can take an input, right, the returns input, and then it can take any other object. In this case, we chose the same object, and transform it. And that is a transformer in scikit-learn. Okay, a function, we instantiate it, we fit it, and then we use the fit function to transform something else. That is ingredient number 1. Okay, let's move on. We can use one-hot encoding. Okay, so we list the values we want to see. These are the values that we have. The listing exchange takes values N, Q, A, and P. And then we can get from scikit-learn one hot encoder. Okay. We use the same procedure. We import it from a certain place in scikit-learn. We import the class. We instantiate the class. We did the same thing above, right? And then we fit using a certain variable. Okay, so we fit one hot encoder, and then we can encode the same mechanism, right? The same set, and we end up with 4 columns. Some of them are going to be ones, some of them are going to be zeros, because the first few observations, have this value equal to 1, and then the rest of the values equal to 0. So every row will have one and only one. It's a one hot encoding. Um, and we have encoded the entire set of listing exchanges. Now, if I wanted to use this for logistic regression, I can say which value we want to drop. So we can drop the first value, or we can drop any one of the values if the values are binary. So I'm going to drop the first value. Okay, and so you can see what it does. 1 hot drop equals first. Okay. And I'm going to see how it has been modified. Now it's part of the instantiated object. And when I do the transformation, I only end up with 3 columns as opposed to 4. So this is a dummy transformation. And this is how you get from a one hot encoding mechanism to a dummy transformation. So somebody asked, hey, how do I do it mechanically? This is the way you do it. You drop the first one. Doesn't have to be the first, the last, the nth. Doesn't really matter, right? Okay, let's move on. Now I will introduce the concept of a pipeline. We have a one hot encoder that will apply to some variables, the categorical variables. We have another transformation, the standardization procedure that will apply to the numerical variables. We need to create something that embeds the logic. Apply this for categorical, apply that for numerical, and then for everything else, do nothing or do something. Like, we make the choice. And this concept is called a pipeline on one side, and then I will introduce a column transformer. Okay, so I'm going to load a whole bunch of things. Of course, from scikit-learn.pipeline, I load the pipeline. From preprocessing, I load my standard scaling, a certain model. In this case, it's going to be a decision tree classifier, and then a few things that I will require to evaluate my model. Okay, so this guy you probably have already seen, and these are scoring functions. Okay, so I will give it a true set of values, a predicted set of values, and these functions will return accuracy, log loss, Cohen kappa, and F1 score. For those of you who are not familiar with Cohen kappa, it is a balanced accuracy. It considers the relative weights of your classes in the sample, and it will give you a better notion of what accuracy is, right? So if you recall, the distribution of classes is not great. It's not uniform. We have a minority class over here, so we need to do things to our accuracy measure. Okay. Now, the pipeline is just what it sounds. It is a sequential applications of models. Okay, so the first pipeline, it's going to be a very simple pipeline. I'm going to create it with the word pipeline. So this is my class definition. I open parentheses, and inside the parentheses, there will be a list of tuples. Okay, so I'm going to take this one step at a time. A list starts with square parentheses, right? And it can contain whatever it is that you want it to contain. And in this case, we are going to make it a list of tuples. Tuples are identified by round parentheses, but above all, a comma in the middle. So these are pairs or triplets or quadruplets and whatever, tuples of things, right? Each tuple, in this case, is going to have 2 components, a label that I define. In this case, I called this one hot. In this case, it was originally a KNN, but it's a decision tree. So I can call it DT. I can call it CLF for classifier. I'm just going to leave it KNN, just for so I don't mess up my code. And the second entry is the actual object. Okay, so what I'm saying here is I'm creating a pipeline with 2 steps, right? Each tuple is 1 step. The first step is 1 hot, and it will contain a 1 hot encoder that has this specific parameter called handle unknown equals ignore. So for somebody asked, how do I handle unknown observations? This is how you handle unknown observations. You tell it either ignore them, and I'll show you where the documentation is in a second. Okay. The second step is once I have the 1 hot encoder, I will pass on the results to a decision tree classifier. Okay. So the decision tree classifier takes a certain parameter. The criteria is going to be the entropy, so not Gini coefficient. I'm going to use entropy. And the max depth, this is a regularization parameter, is going to be 3. I'm going to use these words over and over again for the next 3 days, so don't feel concerned if you don't understand 100% of what I'm saying. Okay. At the end, I'm going to end up with a pipeline. Oh, I forgot to run this code chunk. So now that it's loaded, I will end up with a pipeline. And a pipeline is just what it sounds. Step number 1, step number 2. Okay. I'm going to take a few categorical variables. So I'm going to say listing exchange and market category, or there I'm going to put them as predictors, as features. They are both categorical variables, and my target is the target. Will tomorrow bring a positive return or not? I am a trader. I need to make my bets today because tomorrow I want to make money. Okay. So I create a testing and training sample using my train test split function. No surprises here. I use my random state of 42 because I want you to be able to replicate my results. And I take a test size of 20%. Okay, so 20% of my sample will be reserved for testing, and the rest is going to be for training. And I fit my pipeline. And this is the key. I issue a single fitting command, and it will be distributed to all of the elements in my pipeline. It has already encoded and trained the 1 hot encoding, right? And it has also trained the decision tree classifier in a single step. This is what will guarantee that I am only applying my 1 hot encoding mechanism to my training set without contaminating my testing set. And that is the reason why I insist we need to use the pipelines, because they will keep us safe from contamination between training and testing set. Okay, let me just move on with the example. I can predict. So I take my pipeline, which has already been fitted, and I can produce predictions. If I use my training set, I will get training predictions. And if I use my testing set, I haven't touched it until now, I will get testing predictions. Okay. So I have produced my predictions. Okay. Now I can also use this function, predict proba, which is a standard output of your classifiers in scikit-learn. Despite the name, this is not a probability. This is the thing that I was insisting. It is a score. I'll fish out the paper. I'm more than happy to share it with you. But there's no assurance that this will be a calibrated probability. Okay, so just remember that. I'm going to get my probability metrics. Why do I need them? Because some performance metrics will require a probability and not only a label. Okay, now I'm going to open a dictionary, right? So lists are square parentheses, tuples are round parentheses, dictionaries are curly parentheses, okay, curly brackets. Now, I'm going to store all of my accuracy, Cohen kappa, log loss, and F1 scores, so all of my performance metrics in this dictionary, okay? And I'm going to give it whatever it needs. So if I am evaluating against a training set, I'm going to give it the training predictions. If I'm evaluating against the testing set, I'm going to give it the testing predictions, okay? And I click here, and you see my not very impressive results. I get an accuracy score of 55%. Great. As a trader, I would say, hey, I'm making money. right? More than 50%, that's good enough for me. And then I observe my Cohen kappa, and I say, no, you know what? Scratch that. I am getting 0% accuracy here, balanced by the relative frequency of classes. Log loss is 68%, both on training and testing, and F1 score is 0. Horrible model. Don't use this model. Like, flip a coin. It's much better than using this model. Okay, so obviously it was a very bad model, right? I didn't use a lot of things. Okay, so I'm going to use 5 minutes, more minutes of your time, and I'm going to just finish up this discussion. We want to use all of our data, right? So now we need to figure out a way on how to incorporate our numerical features, because we now have a pipeline for categorical features. So now the strategy is going to be, data comes in, I'm going to split between numerical features and categorical features. After that split is done and I do my pre-processing, I'm going to rejoin my data and I'm going to send it to my classifier. Okay, so the thing that I'm going to use to achieve this is called a column transformer. Okay, so I load my column transformer, same mechanics. The column transformer will take as inputs different steps, which are a list of tuples. Once again, list of tuples. There's a recurrent theme, right? These tuples have 3 components. Name, the step, the actual function for the step, and the variables that I want to apply it to. Okay, so name, the step, and the variables I want to apply it to. So notice what I'm doing here. I'm saying, hey, this is a numeric transformer. The transformer is going to be the standard scalar, right? And I want you to apply it to my numerical variables: returns, volume, open, close, and high and low. So all of these are numbers. I can standardize them. I can operate with them as numbers. Then this other part is going to be one hot encoder, right? In this case, I'm not going to ignore the unknowns. I'm going to handle them if they are infrequent, right? So this is yet another option. And I'm going to apply this to my categorical variables, okay? Anything else that is not in these variables, drop it. Ignore it. Discard them. That is one option, right? There are other options for remainders, so I'll show you where to look for the options. We're going to return to this procedure several many times. And then I take my pipeline. And in my pipeline, in the pre-processing step, I'm going to plug in my transformer, my column transformer, the thing that splits into 2. And then I'm going to apply my decision tree classifier, okay? And what I get is this nice pipeline that contains my column transformer. This is the 2 splits that I have, and then my decision tree classifier. If I check, this has not yet been fit, right? So I haven't run the fit command. Therefore, this is only a plan for execution. Nothing has been learned. Nothing has been executed, okay? So now we want to apply something called cross-validation. And show of hands, have you seen cross-validation before? Yes? Brilliant. Okay, so I'm going to assume that this is general knowledge. Basically, cross-validation, I divide my sample into different chunks. I select one, that is going to be my validation. I use everything else for training, and then I repeat, right, with all of the different chunks. What I'm going to do here is I'm going to take my a certain function. So I'm going to create a function that is called evaluate model. It will take a certain classifier, right? So it's just a model, a generic model. I'm going to take also some data, train, testing data, and I'm going to do all of the calculations that I did before. And I just put everything in a function because I want to run this many times. Okay, so this would do nothing. I just created a function. Now, my schema is going to be my numerical variables, my categorical variables, and my target is my target. I do exactly what I did before, right? I split into train and test, and then I split again because I want a validation set and a testing set. Okay, so I'm gonna train, validate, and test right now. Okay, so I'm gonna run this, and then I'm gonna evaluate my model. Notice that I'm sending a certain pipeline, version 3. This is the pipeline that I have over here. Oh, sorry, different pipelines, creating pipelines. And it's a pipeline here with a certain set of parameters. Okay, so I'm gonna define the parameters over here, and I'll come to the parameters in a second. But I'm just basically gonna evaluate it in this code chunk. Okay, and I get some results, not great results. You can compare them with our previous results over here. Complicating factor over here is just basically this thing here. I am sending in certain parameters to one step in my modeling pipeline. That step is the decision tree step. Remember, we explicitly made this label. We selected the label. And within that classifier, I know that there's a certain parameter called max depth, and I want to make it equals to 3. And I do that by using this set param command with this ** form and a dictionary after. Okay, I'll come to you, Maria, in a second. I just want to show you that this step is called decision tree because I named it decision tree. Maria, please.
Sorry for interrupting. Just a question about the notebook that you are using. I see that you're on branch live.
Ah,
So-
yes. So I can commit to the live branch once I'm done with this lecture, and
Oh,
you
okay,
can
okay.
see everything that I wrote and why I corrected and such.
Okay, but the notebook that we should be using is the one on main?
Yeah, it's the base on this. So
Okay.
everything that I did live is going to be committed to that new branch called live.
Okay, okay. Okay,
Okay.
thank you.
No problem. So we're here. Okay. Now we can change the parameters. So I just change it to a different parameter set, and I get a new set of results. And the only thing that I have changed is the maximum depth of that I'm allowing the algorithm to go, and I will generally get a different set of parameters. Notice in particular that my loss has actually increased quite a bit. Okay. Now, finally, cross-validation. We're going to perform cross-validation. There's nothing mysterious about cross-validation. The first thing that I'm going to use, and this is the only time that I'm going to use it, is this nice function called cross-validate, to which I can give it a classifier. In this case, it's going to be one of our pipelines. I'm going to give it an X, Y data frames, right? We're going to tell it how many times we're going to perform the cross-validation, how many folds we're going to have in our cross-validation result, the type of scoring mechanism that I want to use. So I use all of these different scores just because I want some diversity. And I also want to return the training score. Okay, so I'm going to run this. And actually, I'm going to start running these cells again as well. The reason why I do all of this manipulation is because this set of results are going to come in the form of a dictionary. And dictionaries, although they are very convenient, we can output them as JSON files and whatnot, they are difficult to read. So the easiest way to read them is just to plug them into a pandas data frame, and then you will get a very nice table, right? So that's the only reason I do it. I will do it twice, one for a tree that has a maximum depth of 3, and then once again with a maximum tree of 15. Okay, so these are the results of the tree with the maximum depth of 3, and now it's running for the other one. I get a lot of information out of this, and we have discussed all of these metrics. How long does it take to fit the model in each one of the iterations? How much does it take to perform an inference? This might be a useful number for us. And then test accuracy, train accuracy, test of one, train of one, and all of my metrics, both on the testing side and on the training side. Remember, the testing refers to that fold that we labeled as the testing set. Okay, we will get it 5 times because we asked for 5 folds, and we get it again for the 15 depth decision tree. Okay, I'm going to pause here because we're at time. Oh, one last bit. We can calculate the average just by doing the mean result like this. And this is usually what you will want to use to make your decisions, to evaluate your models. the sequence would be, I kind of have an idea of what the pipeline should look like. I will determine certain regularization parameters. I have already chosen a certain performance metric, and then I change my performance parameters. Perhaps I change my entire pipeline, and I evaluate always against the same metric, right? In this case, I want to use perhaps log loss, which is here, or I may want to use something like ROC AUC, or whatever your choice is, but you need to stick with that choice across all of your experiments. Tsui, please.
Can you scroll up? Just I want to check if we have comparable results, because mine are evaluating faster. So if you go down to for the sort of the data frame for the D15 dictionary. Okay, so there's more variability in the fit time of the D15 dictionary than there is of the D3 dictionary. Like,
meaning the standard deviation of these things?
yeah, so like in the fit time, it's because there's just more, there's a larger range of values. Or actually, is there? Because okay, so here's another thing. The time is different on my computer. So is that something that I would encounter just because if I have a different computer? Okay.
Yeah. And also between your computer and the production machine, right?
Okay. Yeah. And so basically, but we would want to evaluate based on the best performance of the production machine.
That is correct. But generally, you will find that if it performs faster in your computer, it will also perform faster in the production machine. Perhaps not the same amount of time, but whatever is better on one side will tend to be better on the other.
Yeah, because in my machine, D15 is performing not quite a bit, but it's performing like under 2 seconds.
That's entirely possible. Yeah.
Whereas D3 is performing over 2 seconds for the most part.
Yeah. That's entirely
So
possible.
that's normal? Okay.
Yeah. And there's no assurance that you will get the same performance as I. Using an older laptop, I use this laptop only for teaching, so it is kind of like an extra laptop that I had.
Okay.
So
got it.
Yeah. Any other questions? No? Okay. So just as a preview, this will. Oh, sorry, Antonio.
No, sorry, very short, not super relevant to the subject. I always follow your code from main, but today, just because you mentioned that something in live was updated, then I was not finding you and whatnot. What did you say was updated from live?
Oh, no. I will update after the class. All of this code, you will have it on live, and you will be able to see my annotations and playing around and all that stuff.
As usual. But at the beginning, you said that something.
Oh, this library, this notebook has been updated in the main branch.
Oh, in the main one. Okay.
Yeah, exactly so.
No problem.
Okay.
Thank you.
No problem. Sneha, please.
Yeah. So I have a question regarding fit and transform. So when you were using fit transform function, is there a reason that you used fit and transform separately rather than using
fit transform?
Transform, yeah.
Yeah. Didactics, because I'm teaching. So the Sneha's question is related to why did I use fit and then transform if there is a function that does both at the same time, right? So you can fit and transform in here. So I can do something like fit transform like this, right? And the answer is yes, that is entirely possible. It's a convenience function. It fits using that data and then transforms using the same data. And the answer is just because I wanted to demonstrate that there are two functions. Fit transform, it's sometimes used, but it's not for machine learning. It's just for performing the transformation, PCA, and that sort of stuff. Yep.
Okay. And another question is, like, if you scroll up all the way to the top, I noticed that you used inside glob function, you used concatenation. And in the first lecture, or maybe the second lecture, you said you recommended that you should use join.
Right? The LTS chart. Yes, I didn't observe my own recommendation. I should be using OS path join, something like this, right?
Yeah.
Yeah, you're absolutely right. This is a better option.
Okay. Thank you.
Okay, my pleasure. Okay, so we're gonna do this many times, and we're gonna do it so many times that we will need a database backend to keep track of our results, right? So as you can see, very simple experiment. It was a very simple pipeline. There's really no complicating matter here. We ended up with a little data set of results. So the data set of results is this one here, right? And then we ran another experiment and we just ended up with something of equivalent size. And we will do this many hundred times, right? It's not uncommon to test a few hundred combinations of parameters across different models. So at some point, you need appropriate data infrastructure to record your results and also to keep track of where is it? These guys. These things are binary objects that contain the model itself, and I can save them and distribute them. There's no reason to say, hey, I will store the parameters and then use something else to train the model and then bring it back and so on. No, you can directly save the trained model and make it available to your users or use it for deployment at a later stage. And that is where MLflow kicks in. We're going to discuss it in our future sessions, and that is what follows. Okay, so this is a training pipeline. I hope you have learned something useful today. Is there any other question?
Just one last question. This is over here. So regarding the pipelines, you've mentioned saving them. Those would be part of the Docker's environment when you deploy them in production. Is that correct? Okay.
Yes. You can also use a pickle format that is a standard format in Python. So you do pickle dumps or pickle load, and that way we convert into a file and restore it from there. I can show it once we have a proper model, how to do it manually. Okay.
All right, excellent. Cheers, thanks.
Brilliant. Any other questions? Going once, twice.
So, is this one, the pickle is the other format. So does this pipeline is portable as well?
Yes, yes. All the scikit-learn models are serializable and they can all be pickled.
Okay.
Not every modeling library allows you to do this, so you just read the documentation. But scikit-learn, everything is serializable and pickle.
Okay. Thank you.
Okay.
Got it. Thank you.
Excellent. Anybody else? No? Antonio.
I have a question either for you or for learning support. For installing Docker, when I go to the webpage, there is two options. Download the link directly from the webpage and download the link from Microsoft Store. Which one is more recommended?
I don't like the Microsoft Store, but that's a personal preference. I downloaded the one from Docker website,
Okay.
and that is the one that I'm using, but it's up to you. Both should work.
Okay, good.
Okay.
And just like completely non-important suggestion, like from the live branch, one option could be to delete the things that they have not been live yet. Meaning files from 4 to 7, they could, it's a stupid thing, just delete anyway.
Yeah, no, I hear what you're saying. Yeah, I'll get better at uploading my live notebooks. This is the first time I do it, and so thank you for the recommendation. I appreciate it.
Great session. Thank you.
Thank you so much. I'm gonna pause the recording, team.